Hi everyone, fluid mechanics. Let's solve an interesting problem in dynamic viscosity in a fluid. So in this example, we want to calculate a torsional torque induced by shearing stress for a cylinder called shaft, which is rotating inside a bigger cylinder. The radius is capital R, height of cylindrical shaft is h, distance to the side are alpha, and distance to the bottom is beta. And within the two shafts are filled with an oil. We want to see what is the torsional torque when it's rotating on the bottom part and also at the sides. Let's see how we can approach this problem. So first of all, for the bottom part, if we just take an elemental, this is the top view. If you look at the problem, this is the top view. And if you just take out this small reddish element by the radius of r and the thickness of dr, then dA of this narrow strip is 2 pi r dr, and at the same time tau shear stress in fluid is equal to mu velocity over thickness. So our thickness definitely is b, mu is dynamic viscosity, rw is when it just keep in rotation, that's the angular velocity. So h will change to b for the bottom part. That's the distance between the bottom of our gold cylinder to the bigger one. And then df force is tension stress times the area. So df is tau dA. And if we call it the bottom torsional torque dt1 for bottom, that's r times df. A moment is an arm times the force. So the dA, we know what dA is, what tau is for in terms of formula. And then if you replace in dF formula, that's 2 pi r squared dr mu w over b. And then definitely differential form of torsion for the bottom is rdf. And then if you integrate it from 0 to r, from the center to the side, it just gives you the torsion at the bottom. Then if you do the integration to the mass, it just gives you this numeric value for torsion for the bottom. So T1, which stands for the torsional torque of this shaft in rotation, that's pi mu w over 2b, which is the distance from the edge to the bottom, and r to the force. That's T1, and let's see how we can calculate the torsional torque for these sides. So for the side, so if you just consider an element in this part and calculate the area for that, that's 2 pi r dz, and that's and this time the h or b moves to the side. Instead of b, it just moves to alpha because we are working with the sides right now. So that's rw mu rw over alpha. That's our shear stress, and our element for area is 2 pi r dz, this element. And this time we integrate it like vertically from 0 to all the way down the overall height of our cylinder. And then df definitely stress times area is force, and then dt2, the element of torsion for the sides are rdf. And if we do the integration, is just alpha is just for the sides, sits in the denominator. And then if you Integrated is just, this is a constant and integrated from 0 to h dz. And we integrate dz from 0 to overall height. And if you do so, it just gives you that numeric value. And for make of comparison between bottom and side torsion due to shear stress, we can have like T1 for the bottom, that's pi mu w over 2b times r to the fourth, and for the side, the equation of torsion, the torsional torque is 2 pi mu w r cubed h over alpha. Thank you. We'll solve more problems.